This is an introduction to section 9.5 of the textbook. It's equations of lines and planes in R3 or in 3 dimensions. Now, there's a whole lot of information in this section. This is just a quick introduction, and I want to specifically talk about using vectors and parametric equations to do equations of lines and planes. Vectors and parametric equations. So in 2 dimensions, we know all about lines. You have y equals mx plus b, right? You have some y-intercept or initial value. You have a slope, and you've got your line. But it turns out that doesn't work very well in 3 dimensions. And so it turns out that vectors and parametric equations work a whole lot better for equations of lines and planes. And so first I'd like to do a quick refresher of parametric equations, and we'll start with 2 dimensions because that's what you're familiar with, and then I'll show in 3 dimensions how this works. And so suppose you have something like x equals 3t plus 2 and y equals t plus 5. So this means that you have coordinates that are depending on some third variable, which we call a parameter, t. And so to graph this by hand, you would just start with t being, say, 0, plug it in, find out what your x-coordinate is. So when t is 0, you have 3 times 0 plus 2 is 2. So your x-coordinate is 2. When time is 0, or time is often what t is representing in parametric equations. So when your time is 0, 0 plus 5 is 5, so your y-coordinate is 5. And so that gives you, on a 2-dimensional surface, you have x, you've got y, so you've got the point 1, 2, 3, 4, 5, 2, 5. Okay, when t is 1, you've got t is just time, and so you can think of it like this, that the x-coordinate is moving at a rate of, say, 3 meters per second, because it's 3 times t. And so you can think of it like your x-coordinate has just increased by 3 meters. So it's sort of like your slope, in a sense. But it's the slope only in the x direction. It's a rate of increase is a better way to think about it. Now, for y, the quote-unquote, the slope is 1, and so that means when time goes up by 1 second, the y-coordinate goes up by 1 point. So now you have the coordinates x is 5 and y is 6. Okay, so you can see that the numbers would just keep on going. You have x keeps going up by 3 points, or 3 meters. It goes up again by 3 meters, and so on and so forth. The y-coordinate just keeps going up by 1 right there. And so this gives us a line because x is increasing by a consistent 3 meters per second, y is increasing by a consistent 1 meter per second, and so we have our slope. But now here's a relationship between parametric equations and vectors. We have our slope, which we know would be rise over run, 1 to 3. But in terms of vectors, we call slope a direction vector. All right, let's put this in right here. So a direction vector. So in this case, you could think of that slope, that little triangle there, the rise over run. Think of it as a direction vector. Usually we use vector v for direction vectors. Is the vector 3, 1, right there. So this is key to understanding lines in 3 dimensions, is understanding direction vectors. It's like a substitute for slope in when you have 3 dimensions. All right, so now we also have what we call position vectors. So let's go back to this point 2, 5 right there. So in 2 dimensions, we just call it a point, which is fine. In 3 dimensions, yes, you can have a point with 3 coordinates, but it's more useful to think of this as a position vector. So that little point right there, the point 2, 5, we will call that a position vector. Now, of course, it is just a point. But you can, but anytime you have a position vector, if you want to think of it in terms of vectors, you can think of it as a vector from the origin right there. So we have the position vector 2, 5. Could put a little arrow and make it even look more vectorish. We have the position vector 5, 6, which is right there. So you can put another line right there from the origin, or a vector, excuse me, from the origin to that point 5, 6. It's just another position vector. Usually we use R for position vectors. And so the 0.25, you would say that's a position vector 2, 5, like that. If you want to call it R1, actually, or R0 maybe, actually would be better because that's for time 0. You can say position vector R1 would be 5, 6, and so on and so on. But anytime in the book you see a position vector, it will be denoted with vector R, and all it is just a point on a line or on a plane or on whatever it is that you're trying to graph. All right, so now let's think of this in terms of 3 dimensions. So if you have an X, Y, Z axis, we'll start off with just some random points on this plane, and we'll call that a position vector, whatever the coordinates of that is right there. And then you can't say, well, what's the slope of that line? Because you can't say the slope is 2/3 or something. So you have some line, but instead of using slope, we use direction vectors instead. So we have some point which we call R0, which is a position vector, and then a direction vector. Let's just say it's something like -2, 1, 3, which just means that we have some point and the line is moving in the direction -2, 1. All right, now the relationship between points and vectors is even deeper. So let's go back to our two-dimensional our two-dimensional example. Back to x equals 3t plus 2 and y equals t plus 5. Let's write that one more time down here. 3t plus 2 and y equals t plus 5. So in parametric form, think of it like x is moving forward at a rate of 3 meters per second, and it's starting at the point where x equals 2. And y is moving up at a rate of 1 meter per second, starting at 5. And so we had that the 0.25 and the line was going off in that direction. All right, and you can convert this into a vector equation. You could think of as any point on this line is a position vector, which we can just have the components be x, y. So that would be position vector R. So vector R is like, it's a variable vector. Oops, I don't want a subscript there. It's just the random, not random. It's a variable which really is 2 components, and in 3 dimensions it'll be 3 components. All right, now that vector x, y, it's equal to the components. Well, x is equal to 3t plus 2, so you can write 3t plus 2. And then the y component is t plus 5. Okay, so 2 vectors are equal if their components are equal. So we see x is literally 3t plus 2, and y is literally t plus 5. Now we can break this up even further. You can say that this is the sum of 2 vectors, right? So we have the vector 3t comma t plus the vector 2, 5 right there, because you're just adding 2 vectors together. 3t plus 2 is 3t plus 2. That's adding the horizontal components. And then t plus 5, excuse me, and then t plus 5 gives you t plus 5 right there. If you want to look at the geometry of this, we have the position vector. I've got position vector plus position vector equals position vector. So I've got the position vector 2, 5, which would be my initial point right there. If you want to make it look like a vector, there you go, right there. But it's just a point. And then you have some other vector, 3t and t, where let's say t equals 1, for example. So then you'd have another vector out there. Or hold on, wait, pardon me. Sorry. Okay, so think of it as 3t and t. Well, that's your direction, isn't it? It's your direction vector. X goes up 3 points, Y goes up 1 point. And then we have two vectors, put tip to tail. And so when you add those two vectors together, your initial point plus your direction, you get that new position vector, which is we'll just call that XY right there. And then for any value of t, you can generate any point or any position vector along that line right there. All right, so let's take this one more step. We can factor out the t here. Let's go back to black here. So I've got vector xy, which is equal to t times 3, 1. So that is the direction vector. It's kind of like your slope in a sense, times your t, and then plus some initial point, 2, 5. And so in a sense, it is y equals mx plus b, like we have with two-dimensional lines, where your slope is, I'll put all these quotation marks because it's not really slope, but it's the direction vector times your x, but now we're calling it t, plus your y-intercept, but it's not really y-intercept, it's just some initial point. And then that is equal to the output, or the dependent variable, which we could call y right there. So it's a very close relationship to slope times x plus initial value equals y. However, we change the letters around. Xy, that is a position vector. It will equal a direction vector times t. So often that, well, actually it can go either way. All right, so t becomes like a scalar multiple. So t times a direction vector, and then plus an initial point, which we will call a position vector, r0, right there. Now this is in your book, this equation, except I think they put r0 first, but when you add, it doesn't matter. And that's the beginning of how the equations for lines work. The rest of the videos will explain the details and give examples and so on.